Hello, greetings from Thurles in County Tipperary. We're marking the Tipperary Festival of Science this week here, which is taking place during Science Week. Okay, I'm going to tell you a bit about the Platonic solids. So what are they and why are there only 5? So you can see here on your screen we have the 5 Platonic solids. This is a nice little applet that you can find on GeoGebra. And I should acknowledge the author, who is MMK Savall. So what are these Platonic solids? So we can see there on the top left that you've got a cube in green. We have the dodecahedron there in pink, just to the right. Coming down to the next row, we have in yellow there a tetrahedron. And beside that in blue, we have an octahedron. And then finally, on the bottom right there, an icosahedron. So what's so special about these solids? What is it that makes them the Platonic solids? Well, first of all, they have the property that each face is a regular polygon. So let's have a look at that. So if you look at the cube, each face of that cube is a square. Now, if we look at the pink dodecahedron there, each face is a pentagon. And moving down, the 3 solids on the bottom row, in each case, the faces there are triangles. Okay, they're regular triangles, equilateral triangles. So that's one defining property of these Platonic solids. They're built out of regular polygons. Second property is that if you look at any corner of any one of those Platonic solids, it looks the exact same as every other corner in the solid. Okay, so if you were to pick the cube, for example, you look at a corner there, you can see that you've got 3 edges coming into that corner. And if you look at, it doesn't matter which corner you look at, it'll always look the same. Okay, and that goes for all of the other polyhedra there. Okay, so what I'd like to do is tell you a bit about why there are only 5 polyhedra. Now, this was known back in Euclid's day. You can find the Platonic solids in Euclid's Elements, but I'm going to focus a little more on the combinatorial aspects of Platonic solids. So the properties that come about just by counting vertices, edges, and faces. Okay, so let me introduce a little bit of notation here. I'm just going to scroll down. So first of all, K here is going to denote the degree of a face. What do I mean by that? I just mean if you take a face of any of these polygons or any of these Platonic solids, you can count the number of sides in that face. So for example, for the cube in green, pick a face. The number of sides, well, it's a square, so the number of sides is 4. So there, K is equal to 4. Next piece of notation, D is going to denote the degree of a vertex. Now, that's just another way of saying it's the number of edges that are coming into that vertex. So again, if you pick the cube and look at a vertex, there are 3 edges meeting at that particular vertex, no matter which vertex you choose. So I'll denote that number by D for each Platonic solid. V is going to denote the number of corners, or in more technical language, the number of vertices of a Platonic solid. So the number of corners. E is the number of edges. So an edge is where 2 faces meet. Okay, so E, we're just going to count up the number of edges. If you want to pick an example, say the tetrahedron there in yellow, you can count up the number of edges. We have 1, 2, 3, 4, 5, 6. 3 in the base and then 3 sort of sticking up. F will be the total number of faces. So these are the flat surfaces that we're looking at. So again, we can just count those up and we'll call that number F. Okay, so here's a little activity, and if you want to do this yourself, maybe pause the video at this point and try and fill in this little table for yourself. So I've listed there the Platonic solids down the left-hand side. Along the top here we have the values K, D, V, E, and F that we've just introduced. So for each Platonic solid, see if you can fill in those numbers. Once you've done that, see if you can compute the value V minus E plus F, and we'll discuss that in a moment. So now's a good point to pause if you want to try and do that yourself. If not, I'll just continue on. Okay, so let's see what that table looks like when it's filled in. Okay, so I've filled in all the numbers here just by counting. So number of faces, degree of each vertex, number of vertices, number of edges, number of faces. So filling in that table, and then I've computed V minus E plus F at the very end. If you've done this correctly, you should get these numbers, and you should spot a pattern has emerged in the right-hand column here. No matter which Platonic solid we chose, we're just getting the value 2 every time. So there's clearly a pattern, and this is where mathematicians start to get excited and they say, oh, I've spotted a pattern, maybe there's a theorem there. So in fact, there is a theorem. It goes back to Euler, and it says that v minus e plus f is always equal to 2. This is for all, well, you could say so for all planar graphs or for all convex polyhedra. And that's what we're observing here, basically. So for these particular solids, this equation always holds. Now I want to introduce two other little lemmas. One is called the handshake lemma. And what this says is that if you count up the number of edges in any of those solids, then multiply it by 2, that's the same thing that you get if you add the degrees of all the vertices. So that symbol is called sigma, and that's a fancy way of saying add what comes next. Okay, so that's the first little lemma. The second lemma, we'll call it here the border lemma. It gives you another way of counting. So it's telling us that 2 times the number of edges is equal to the sum of the degrees of the faces. Okay, so again, the sigma notation is used there just to denote we're adding things. So we're going to use all of this information, these two lemmas and Euler's theorem up here, to argue that, well, there can be only 5 Platonic solids. There are no others that satisfy these defining properties, that they are built by regular polygons and that every corner looks the same. Okay, so how do we go about it? Well, the first lemma tells us that the number of vertices is 2 times the number of edges over d. The border lemma tells us that the number of faces is 2 times e over k. Now we bring in Euler's formula, so we bring in this equation that we observed from our table, v minus e plus f equals 2, and we plug in these values for v and f. Okay, so we just plug them into the equation. We can divide across here by 2e, and we obtain a new equation, and I'm going to put a little star beside that because, well, it's an important one. And what we can see here, the key thing to notice here is that the right-hand side of this equation is 1 over e, which is a positive number. Okay, it's always a positive number. On the left-hand side, well, we could have a positive number or a negative number. It really depends on the values of d and k. So if d is a big number, then 1 over d is very small. If k is a big number, then 1 over k is very small. So when d and k are both very big, it's very possible that what we have on the left-hand side is actually negative, because we subtract 1/2 from some very small number. Okay, so that's giving us a clue that there's only certain values of d and k that are valid in this equation. So we can explore that in more detail. If d and k are both bigger than 3, then yes, the left-hand side will have to be less than or equal to 0 here. Okay, just by plugging in values for d and k here and just observing that in those cases, yes, 1 over d plus 1 over k is smaller than 1/2 or less than or equal to 1/2. On the right-hand side, of course, it's always positive. So that's not allowed. That can't happen. So now we consider what else could happen. If d is equal to 3, or if k is equal to 3, well, what we're saying is d has to be equal to 3 or k has to be equal to 3. There are no other possibilities. So if k equals 3, then we plug that into our equation and we notice that, again, d can only satisfy certain values for that equation to make sense. Those values are 3, 4, and 5. Similarly, if d is equal to 3, then k can only satisfy certain values, 3, 4, and 5. So we can list these possibilities. There are the possibilities that d is 3, k is 3, d is 4, k is 3, d is 5, k is 3, d is 3, k is 4, or d is 3 and k is 5. They are the only possibilities, and they are exactly the values that correspond to our 5 Platonic solids. Okay, so there are no other possibilities, and that is why, well, this is one reason why there are no other Platonic solids. Okay. Thank you very much.